my whiteboard. Okay, so today's lecture we actually center on continuous probability distributions. Of course, you know, on Monday we actually started continuous probability distributions. Of course, you know, I told you the other time, you know, when you have a random variable, the random variable can be discrete or continuous, or discrete when it can be expressed as a whole number, and continuous when we believe that, you know, that can actually lies in an interval. Okay, we're talking about situation where the possible values of random experiments, okay, cannot be counted. And of course, we can only seek out to get the probability of the random variable that lies in the interval. Okay, so as we have a discrete type probability distributions, we also have continuous type. Of course, in a discrete type, of course, you know, I walk you through Bernoulli binomial, hypergeometric negative binomial, and so on like that. So we also have continual type distribution. Okay, so today the focus is going to be on the uniform and normal distribution. Okay, so you know, the outline is going to be, like I said, the focus will be on the uniform and normal distribution. I'm also going to give example. You know, having a discrete type distribution, of course, we basically going to have a common way of making statistical inference. Having a continuous probability distributions, we also going to have a kind of way of obtaining the whether expected value of X or the variance or something like that. So the same thing with, you know, in the United States, you know, you have the East Coast, right? Okay, the state in the East Coast, you're talking about the New York, the Connecticut, and the likes, New Jersey and the like. And if you want to talk about in the Midwest, you know, you have the Minnesota, Wisconsin, Illinois, Michigan, and so on, like that. So the same way we also have discrete type probability distribution, continuous type. So we're going to be focusing on uniform and normal, like I said. So looking at the uniform distribution, you know, the other time on that discrete type, I introduced it to discrete uniform. We also have discrete normal. We also have discrete uniform. I'm going to say that again. You've been introduced to discrete uniform. Okay. We also have continuous uniform. Okay. So what I'm presenting to you now is a continuous uniform. Now we actually use distribution to model the outcome of a random variable that we believe is equally likely. Okay, we use this when you are tossing a coin. I'm talking about a fair coin. Okay, with head and tail. Okay, the probability of any side showing up is basically going to be the same with the other side. The same thing with when you are flipping a balanced die. Okay, it's also the same. So you know, I told you you know, on Monday that if I'm seeking to get the probability of a particular continuous random variable, a variable that lies in an interval, I'm actually need to integrate a function that we call a probability density function. So for uniform, the probability density function is given as this. The beta is going to be the upper bound, and A is going to be the lower bound, just like having a maximum and a minimum. Okay, so I told you the other time it doesn't really matter. S can lies in inner B that is close at both end. Okay, open at one end, close at one end, or open at both end. It doesn't really matter. okay? And of course, given this kind of distribution, okay, we actually we can derive the mean to be this and the variance to be that. Give me 1 second. I'm actually okay. Let me just trying to make use of my pen right now. Okay, so for instance, I basically want to derive this guy. Okay, if I want to derive that, of course, you know, for a continuous random variable, if you want to recall, based on what we did on Monday, okay, so we basically gonna have x, okay, and f of x, okay, ds, okay. No, we actually have this as the formula of obtaining the expected value of x in a situation where we are the x is continuous random variable. So right now, if I basically want to get the expected value of a uniform distribution, okay, so what I'm basically going to use now, I'm going to go from A to B, which is actually the state space, okay, X. And of course, the f of X is basically going to be 1 over B minus A, okay, ds. So take a look at that. So the moment you integrate that and you actually use B and A on that, you're basically going to derive this. So what I'm trying to tell you now is that is the same as the expectation of X. So take a look at that. And similarly, you can also derive the variance, okay? So this guy here now is actually the variance of X. And if you basically want to do that, don't forget that's in class on Monday. Uh, even before, I told you the variance of X, okay, is basically expected value of S squared, okay, minus expected value, okay, of X, okay, or squared, okay. So now you've gotten the expected value of S to be this. You're just going to square that here. But how are you going to get the expected value of S squared? If you want to get the expected value of S squared, if I put squared here, I'm also going to put it here. So which means if I want to find the expected value of S squared, I'm just going to put square here and I'm going to put square here. Okay. Then I'm going to integrate all of that, put the result here minus the square of the mean. That will lead to this. So you can try that. Okay. So what I'm going to say now is that, okay, if we got a random variable x, that follow uniform, okay, or what I'm just going to do, okay, what I'm just trying to say is the expected value of x is going to be this, and the variance of x is going to be this. And of course, if you have the variance of x, you can actually figure out the standard deviation, by taking the square root of the variance. Okay, so I think I'm going to clean my screen now so that I can go to the next slide. Okay, so like I said, that is uniform. Okay, distribution. Okay, okay. So the next thing I actually want to show now, take a look at the example that you have. Okay, looking at that example now. Okay, what values of R make the following uh, you know uh, to be what I call a valid density curve. Okay, so if I basically want to have that, okay, so you can take this as an exercise. Okay, now the takeaway is just that, okay, the density function of a uniform distribution is actually 1 over B minus A. So which is basically the height of the rectangular form, because uniform can also be equated to be rectangular distribution as well. Okay, so now there's another example here. Suppose that X follow continuous distribution, okay, it's uniform to 7. So the way this guy actually walk, okay, when you pay attention to this guy, okay, it means A has already been given to be true. So the first value is going to be A, and the second value, okay, so the second value is basically going to be 7. Okay, now here I said find the PDF of X. Okay, and of course, based on what you are given the other time, the PDF is basically going to be 1 over B, okay, minus A. Okay, so by the time you plug in this guy now, okay, the f of S is going to be 1 over 5. Okay, so which is going to be 7 minus 2, right? Okay, so 1 over 5, that's a constant function, right? So by the time you plot, okay, by the time you plot all of that, okay, whether between maybe this is 2 and this is basically 7, okay. Now they actually from 2 to 7 within that range, okay, the probability is actually 1 over 5, okay. You can see it has a constant probability or true, okay. That is exactly what we mean. And of course, because you already know the parameters in a uniform distribution, okay, let's A and B, now here 2 and 7, okay, or finding the mean, it's basically going to be easy because you know the formula for mean, okay. Don't forget the mean, okay, which is the expected value of X, okay, equal, A plus B, okay, over 2. Okay, so the A plus B over 2 is just like you're going to do 2 plus 7 over 2. 2 plus 7 is going to be 9, right? 9 divided by 2, that's going to be 4.5. And if you want to get the variance, because they ask you to find the standard deviation here, so the variance is going to be, B squared, it's going to be B minus A, okay, all squared, okay, divided, give me 1 second. Let me make one clarification. If you take a look at what we have exactly, so B minus A all squared divided by 12. So now you just plug in the values, then you're going to get the variance. And the moment you get the variance, take the square root of the variance. That will give you the standard deviation. Okay, so another thing that you can actually do is you can make an inference, okay, using the probability density function of a uniform distribution. I think I'm going to erase this now so that basically going to walk us through, okay, so how to really figure the other guy out. Okay, so give me 1 second. Okay, so if you take a look at this guy now, determine the probability of X lie between 3 and 6. I told you the other time, for continuous random variable, it doesn't matter whether it is close, open, or close, close, open, open, provided you have the lower bound, the upper bound, the same, that there's no problem about that. Okay, so what I'm going to do now, okay, if I want to figure out this guy, so what I'm actually going to do, okay, take the integral, okay, 3 to 6, okay, 3 to 6, and don't forget 1 over 5, okay, based on 2 and 7, then the X, okay. So when you integrate that, okay, of course, when you integrate that, that's going to give you X over 5, right? Okay, you have S over 5, then you're going to you got 5 and 3. So that's basically going to be 6 minus 3 all divided by 5, and that will give you 3 over 5. Okay, if you want to do greater or equal to 5, okay, of course, you're basically going to go from 5. Okay, what is the end point? You're going to look at the end point. Okay, that's going to be 7. Okay, then you're going to do 1 over 5. Okay, or the x. Okay, and if you want to do if you want to find the probability of x equal to 4, I told you the other time, okay, the probability that x is going to be an exactly a value, okay, if x is a continuous random variable, it's basically going to be 0. Don't forget that. Okay, so the next thing I want to work on now is what I want to work on now is take a look at the D. You know, we also solve equation. Okay, we solve equation here because when you actually take a look at this particular question now, okay, it says find the value of C such that the probability of x lie between 2 and C equals 0.4. Okay, so it doesn't really matter whether they are closed at both end or open at both end or open at one end. It doesn't really matter. Okay, now if I want to solve this problem now, okay, I'm actually going to write, give me 1 second. I'm actually going to have integral, okay, to C, okay. Don't forget, I'm still using 1 over 5 because of the fact that the parameter is from 2 to 7, which is going to be 1 over 5, 1 over 7 minus 2, which is this, okay, the x. But right now, the probability has already been given here, okay? So all what you just need to do, integrate this guy. Okay, so integrate that guy now. You're basically going to have x over 5, then going from 2 to C, okay? So which is going to be C minus 2, okay, divided by 5, equal 0.4. Okay, now you find yourself back in high school now. So all what you're just going to do here is to solve for C. Okay, when you solve for C, okay, multiply 5 by 0.4, I think that is going to be 2, then 2 plus negative 2, that's going to be 4. Okay, so take a look at all of that. That is how you're going to go about that. Okay, so that is that on that. Okay, so uniform, like I said, is kind of easy. Okay, it's kind of easy. Okay, so the next thing I actually want to talk about now. Okay, now before going into normal distribution, I think I need to first tell you the real life application of uniform distribution. You know, I told you the other time that uniform distribution can actually be used to figure out, okay, the probability, you know, in a situation where the outcome is equally likely. I mentioned earlier about, you know, when you toss a coin, okay, I mean a fair coin, or you choose a balanced die, okay, the probability of any of the sides showing up is basically going to be equal. Or you are investor, you go into, you know, investment, and there's the probability of making profit, if it is the same as the probability of making loss, okay, of course, that's going to be seen as a uniform in nature. And if you want to go into, you know, ecological situation, you know, where you talk about organism now, if the optimal, you know, space, okay, organism have, we actually provide them with the resources of being able to thrive well in where they are. Okay, there's going to be reduced competition, and they can really exploit, you know, their territories when, you know, that is distributed. I'm talking about the space now between organisms, distributed uniformly. Okay, so that's all about uniform distribution. Now I want to go into normal distribution right now. and I need you to pay attention. Normal distribution is a very important distribution in statistics, when you are conducting statistical analysis, whether you are in statistics or chemistry, biology, engineering, and so on like that. Of course, this particular distribution is an household name. Okay, so the normal distribution is actually fall under continuous uh random variable. Okay, because we can only seek the value in the interval. Okay, so what I'm displaying now is the statistical architecture of a normal distribution. Okay, so you can see there are two parameters in a normal distribution. Okay, you actually have what I call the mean and the you know variance, or you can say the mean and the standard deviation. Okay, I just wanted to take note of that. So the pi here is actually 3.142596, and of course the exponential is actually that. So those are kind of constant, and of course you can see the state space. But let me tell you this particular normal distribution was actually developed by De Moivre, okay, when it was trying to approximate binomial distribution with a normal distribution, okay. So, but in 1783, okay, Laplace applied this distribution to the study of measurement error. Okay, that was in 1783, and of course in 1809, Gauss actually apply normal distribution to astronomical data. But let me tell you this, the reason, you may want to ask me, okay, so why is it that a normal distribution is very, very important in statistical analysis? And of course, I'm actually have several responses for that. But the main response is when we look at the shape, okay? When you look at the shape of a normal distribution, it is symmetric and it has a bell shape, okay? If you take a look at that, and this actually model most of, realistic situations. If you want to talk about blood pressure now, okay, in a large group of people, we expect few of them to have a low blood pressure. We expect few of them to have high blood pressure, and we expect the majority, oh my God, we expect the majority to have the blood pressure very close to the average. Okay, and that is what you can see. This is the average, the SENRA. Okay, so this actually depicts some real life practical phenomenon. Okay, so like I said, there are two shapes in a normal distribution. Oh, sorry, there are two parameters in a normal distribution. Okay, we got mu, we got sigma. Okay, what is the role of the mu? The mu is just talking about the location. Okay, I know you're familiar yourself with what I call the center of the measure of central tendency, or the measures of location, or average in general. Okay, so the mu is actually a location parameter, while the sigma is a standard deviation, that will enable us to know how spread out is our data set. Okay, and of course, basically you want to be able to know how far apart on average, okay, is how far on average is the mean, okay, to the respective observation. Of course, if you really want to know how reliable is the mean, of course, we need a standard deviation. Okay, so what I'm displaying right now, okay, when you take a look at this guy now, okay, there's a situation we are we have three set of data, okay, and they got the same mean. Okay, as you can see, the center is actually the center of all of them is basically 15. Okay, but the way the data set spread out, okay, it is not the same. So the first one with a purple color has a standard deviation of 2, and while the green one has a standard deviation of 4, and the blue one has a standard deviation, okay, of oh, sorry, let me see. Oh, that's it. That's my bad. The blue one has a standard deviation of 2. Okay, the green one has a standard deviation of 4, and the purple one has a standard deviation of 6. Because you can see the purple one is the one that is more spread out, okay, and that has a standard deviation of 6. But the blue one, okay, is the one that's, the spread is not that much. You get what I mean? So that's why the standard deviation of the blue one is basically 2. Okay, but when you take a look at the second one now, okay, this guy, okay, you are talking about they spread out the same way. Okay, they spread out the same way, except that they got what I call a different center. Okay, that have a center of 10, and this guy has a center of 15, and the other one has a center of 20. Okay, I wanted to take a look at that. Okay, in the real life practical situation, okay, we could have different data set. Okay, some could have the same mean, and some, and different standard deviation, or the same standard deviation, different means. Okay, I wanted to take note of that. Okay, these are the properties of a normal distribution. Okay, the normal distribution, of course, the mode, the mean, the median, they are approximately the same. Okay, and of course, you know, the mode, which is the point on the horizontal axis, where the curve is a maximum, we occur at x equal to mu, just like what I said. And of course, it's symmetric, it has a bear shape, and not only that, if you want to talk about the point of inflection, actually occur at one standard deviation within the mean. Okay, so, and it's going to be concave downward if the random variable actually lie between this and that. Otherwise, it's going to be concave upward. Okay, it's asymptotically normal, and of course the total area under a curve is basically 1. Okay, I'm leaving this one as an exercise. This is looking like that of a normal. The only thing that is missing here is that 1 over square root of 2 pi something. Okay, so you can try that. Okay, so the takeaway from here is, if I have a random variable, okay, that follow normal distribution, okay, the mean is mu, this variance is sigma squared, and the standard deviation is actually sigma. Okay, and of course, why can't you try that? What I'm trying to say, okay, the expected value of x, okay, expected value of x, okay, you can actually try that, okay, negative infinity to infinity x, okay, and of course, the f of x is basically going to be what I'm writing now, okay. So what I'm trying to tell the world now, if you actually perform what I call the antiderivative, that I call the integration of this, the final result is basically going to be mu. Okay, and of course, when you want to find that of the variance, okay, so that of the variance, that can be done in 2 ways. You can actually go direct, okay, in finding expectation of this guy here. Okay, if you want to go direct to find the variance, okay, so you can do negative infinity up to that, okay, and you have x minus mu, okay, or squared, okay, and when you do that, then you're going to write the distribution now that I call normal distribution. Okay, so I believe you can see that now. So what I'm trying to tell you now, so when you decide to integrate that, that is going to end up in sigma squared. Or if you don't want to go direct, or since you have your expected value of s, okay, you can as well find the expected value of s squared, okay, so which is basically going to be you're just going to put s squared, and you know you're going to put all of that, okay, so all of that you're going to come here, and when you do that, when you obtain the expected value of s squared, okay, the expected value of s squared is basically going to give you mu squared plus sigma squared. Okay, so by the time you use the formula of the variance that we normally use as expected value, okay, expected value of s squared, okay, minus, okay, expected value of x, okay, or squared, okay, so this guy, so I told you this is what you're going to derive. So it's going to be mu squared, okay, plus, okay, sigma squared, okay, minus the square of the mean that you got before. So this is going to be canceled out, right? And finally, you basically going to have sigma squared. So you can try all of that, okay? You can try all of that. Okay, so I want to go into another, you know, one now. So, here now, okay, what I actually want to work on is standard normal distribution. Okay, some of you may be wondering what is the difference between normal distribution and standard normal distribution, and why do I need to standardize my normal distribution? I think I'm going to provide the response to that. Imagine here the other time, give me 1 second. I think I'm going to, let me clear my screen here. Give me 1 second. I'm gonna clean all of that now. So what I want to explain now is why do we need our standard normal distribution? Okay, there's a difference between standard normal distribution and the normal distribution, and of course, I'm going to tell you the reason why we actually need a standard normal distribution. Take a look at this. Imagine a situation where you have set of data that have different means, different standard deviations. Okay, what does that implies? Because does that mean I'm actually going to have, a very huge numbers of statistical tables? Okay, so in order for us to prevent the numbers of, to prevent having an infinite numbers of statistical table, because you know why? If you have infinite numbers of means and infinite number of standard deviation, it means the number of z that we're going to have in the number of statistical table we're going to have is basically going to be huge. So in order to prevent that, okay, we actually going to look for a way to restrict, okay, the mean and the variance, okay, of a of the particular variable we're talking about to 0, 1. Okay, so restricting that to 0, 1 will enable us to have just one standard statistical table. Okay, for those of you, if you have seen statistical table before, if you assert the Z table, you're basically going to see that you have a Z, right, with some probability values. Okay, so the Z that we're talking about, okay, is a standardized normal distribution. Okay, that's an approach now that will enable us to restrict, okay, the mean of the random variable to 0 and the standard deviation or the variance to 1. Okay, so that enable us to prevent, having infinite number of statistical table. Okay, don't forget, okay, got different means. Okay, that goes to infinity, that goes forever, right? And different standard deviation. But with this one now, we're basically just going to have, a constant 1. The mean is going to be 0, the variance and the standard deviation is basically going to be 1. Okay, so this is the formula. Okay, there's a random variable, but let me tell you this, that random variable must follow normal distribution. Okay, normal distribution having mu and the standard deviation. Okay, before I can do that. So in the end, what I'm talking about now, you're going to have a Z now, that's a standard normal, okay, having the mean of 0, the variance 1, or the standard deviation of 1. Okay, so what I'm trying to say in essence is that we can show that expected value of Z, okay, equal to 0, okay, from here. Don't forget, this mu and sigma is a constant, right? So you can decide to show by trying to obtain the expected value, okay, of that guy here. Okay, so if you want to do that, expectation, this is more or less going to be the same as 1 over sigma, right? And you're going to have expected value of x minus mu, okay? And of course, the expected value, this is going to multiply that, okay? So you're going to have expected value of x is mu. Expected value of a constant is a constant, you know that, right? So mu minus mu, okay, times 1 over sigma, that is basically going to be 0. Okay, that was how I said the expected value of a Z, okay, is actually 0. And of course, you can, check that of the variance as well. Okay, the variance of Z. Okay, so the variance, okay, the variance of Z is like, talking about, x minus mu divided by sigma, right? So you actually, if you take a look at that, I can actually have 1 over sigma squared, right? Okay, this one is going to be constant, it's going to come out 1 over sigma squared. Then you're going to have the variance of x minus mu. Don't forget, mu is a constant, right? Which can be written as the variance of x. And what is the variance of x? Okay, it's sigma squared, right? So you got sigma squared divided by sigma squared. So what does that give? So that gives 1. Okay, so that was how you get this guy here. Okay, so so far so good. So basically gonna go to the next slide. So I've already justified the reason why we actually standardize. Okay, you standardize normally distributed variable by trying to restrict the values of the mean and the variance to 0, 1, for us to prevent an ugly situation of having infinite number of statistical table. Okay, now this is not the, some of you, you've come across normalization too, right? Normalization. Okay, normalization is different from standardization. Okay, now by normalization, okay, give me 1 second, I'm actually gonna use my pen now. Okay, for normalization, maybe I'm actually gonna have my Z now to be x minus the minimum value in x, okay, divided by mass, okay, the maximum value in x minus the minimum value. Okay, now this is for normalization. Okay, When I say normalization, I'm not saying that, let me tell you this, if the distribution of the data set is not normal, okay, whether with a standardization or normalization, that is not going to change the shape. That will not make that distribution to be normal. I'm going to say that again. If your data set, for instance, follow exponential distribution or follow Weibull, follow gamma or whatever, that is not normal. Okay, when you standardize, even though with your standardization, with your normalization, you will be able to restrict the mean and the variance to 0, 1, but that does not change the distribution of the data. I just wanted to take note of that. Okay, in case you have a random variable that is not normally distributed. But why, okay, why do we standardize then? Why do we normalize? Okay, variable that is not normally distributed, we standardize or normalize. For example, we standardize, maybe we basically want to dictate, use a z-score to dictate an outlier. Okay, because when you talk about z-score, you're talking about the number of standard deviation from the center, from the mean. Okay, and basically maybe you have a threshold of, when data fall within -3 to -3 sigma to 3 sigma. Of course, that can be tolerated. The moment it is outside that, okay, you can actually say, oh, this is a potential outlier. Okay, or maybe you got so many variables and they have different range, and there's a large difference between the range of one compared to the other one, and you actually want to scale them, just scaling, right? You can actually use the idea of standardization and normalization for non-normally distributed data. But for a normally distributed data, the essence of normalization now, I mean, the standardization now, okay, the essence of the standardization is just, to prevent us from situation where we're going to have several means, several variances, or several standard deviation that will translate into having what I call, so many statistical table, okay, that has solved that problem right now. Okay, if that is taken, I think I've justified, and let me tell you, the idea of a standard normal distribution in statistics, it makes, our analysis very, very easy. Like if you really want to, conduct an inference, okay, that will be tractable, okay, with data set follow normal distribution. Does that make sense? Okay, so this is going to be the statistical architecture, if I call it probability density function of a random variable x that follows standard normal distribution. Like I said, the mean is going to be restricted to 0, the standard deviation, and the variance basically going to be 1. Okay, so we can actually conduct an inference around the standard normal variable, like trying to find the probability of a z less or equal to a. So that is a green shaded part. Take a look at that. So if this is alpha, or if this is a, right? This is a, right? Then this is the left of the high, so that is going to be that. Then I can also find the probability of x lying between a and b, okay, of z lie between a and b, where z is a standard normal distribution. Then we can also find the probability of z greater than a. Okay, let me tell you, whether greater than a or greater or equal to a, they're going to be the same. Okay, don't forget the standard normal distribution is also a continuous type. Okay, so take a look at all of that. So if the shaded part is greater than a, the unshaded part is going to be less or equal to a, because this unshaded part and the shaded part, they're going to be they're going to be complementary. You remember the law of complementary. Okay, by the time you add this guy, of course, to this guy, when you add them up, they're basically going to give you 1. Don't forget the total area under a curve is basically going to be equal to 1. Okay, so I need you to take a look at that. Okay, so I believe so far so good. Okay, so this is I want to find the probability of z greater than a and so on like that. Just trying to show you the picture right now. Okay, if you take a look at this at times, my interest may basically be I'm interested in the probability of z less than negative a, or I'm interested in probability of z greater than or equal to a. But what I'm going to tell you now, okay, this is the same as this guy. Okay, so less or equal to negative a. If I want to change negative a to positive a, then I'm actually going to reverse the sign. Take a look at that. So what we're trying to tell the world is that the area here and here, they're going to be the same. That's what we mean. Okay, as you can see yourself, they're going to be the same. Okay, the area here and the area here, they are the same. Okay, and don't forget when z equal to a, okay, when z equal to a, that probability will be equal to 0. I told you the other time, right? And do you know that if I want to find the probability of z, okay, lie between A and B, where they are open at both ends, it's going to be the same as all this. Take a look at all of that. Okay, they are all the same. It doesn't matter. They're going to be the same because z is a continuous random variable. Okay, so far so good. I'm gonna clean my, give me 1 second. I'm actually gonna erase this guy out now, and I'm gonna go into the next slide. Okay, so far so good. Okay, so I think I've explained all of that. Like I said, now you have an example. Okay, so when z follows standard normal distribution, of course, when z follows standard normal distribution, the mean is going to be 0. The standard deviation is going to be 1. So here they wanted to find the probability of z less or equal to 1.05. Okay, you're basically going to make use of your standard normal table. Okay, so in the evening, make sure you wash out on the canvas. I'm actually going to publish a statistical table. So you're going to check this guy under z 1.05, then you're actually going to read the corresponding probability value for that. And of course, for this guy here, okay, uh, and don't forget, this guy here is the same. It doesn't matter. It's the same as this guy here, the same as this guy here, and the same as this guy here. Okay. Now, if I want to do all of them, okay, well, I can interpret them as z less or equal to 2.38. Okay. Then minus p, okay, less than 1.05. Okay, so which means I'm actually going to go into my statistical table, check for this, check for that, and I'm actually going to subtract the corresponding result. Okay, that is going to solve the problem. Okay, so if you take a look at C, okay, when you take a look at C, okay, the statistical table that we have, okay, the statistical table that we're talking about does not have a greater down, totally have a less or equal to. So what we're going to do, if I want to figure out, the probability of a Z greater than that, okay, so this guy is, I'm just going to say 1 minus the complement. You remember that the opposite of that is basically going to be less or equal to this. Take a look at that. Okay, so when you check for this in the statistical table, you're just going to subtract from 1, then you're going to have your result. Okay, so if you take a look at age, I want to go to age now. Okay, I want to go to age now. Okay, so when you take a look at age, okay, we can also look at the probability of the absolute value of z. Okay, so you need to revise your knowledge of absolute value. Okay, so this guy now can actually be interpreted, okay, as finding the probability of z, okay, lying between the negative of this and the positive of that. Take a look at that. When you have the probability of a standard normal distribution, oh, sorry, because there's a less or equal to, I can actually close that above hand. And in the hand, so all what you just need to do is the probability of, that less or equal to 1. You're going to start with the upper part. Then before you go to the lower part, okay, so less or equal to -1. So what you just need to do is to go into statistical table and check for that. Then you subtract that, that will give you your result. Okay, so I'm gonna erase all of that now. Okay, then I'm basically gonna go into the next slide. Okay, so going to the next slide now. And you can also be asked to find the probability of absolute value of z greater or equal to that. Okay, so when you want to find that, you need to remember that if I have the probability, if I want to rewrite that now, it's going to be less or equal to 2 point negative or 2.45, okay, plus, okay, the probability of z, okay, greater than, okay, 2.45, okay, and don't forget, you can check this from the table, and this guy here is, don't forget, this guy is basically going to be 1 minus the probability of z less or equal to 2.5, okay. So when you get that, then you're going to add that to this guy, then you're going to get all of that. Okay, so I think I basically want to move now to something else. Okay, now I think, well, you can be asked, to actually figure out, giving x equal to a normal, a random variable, or x follow normal distribution with a mean of 1 and the standard deviation of 0.5. They can ask you to find this. Okay, so just take note of that. Then they can also ask you to find, when y follow normal distribution with a mean of -2 and the standard deviation of 5, find the probability of y greater than 0. So if you basically want to find this has not been standardized. Okay, so you need to first figure out your z-score, and that was exactly what I'm trying to say here. Okay, so if I want to find that I need to standardize using this, and if I want to find something between A and B, then I need to standardize that first and standardize that one, and I figure out the probability that z lie between them. So take a look at this guy now. So you're going to apply that. So you need to first get your z, so that I'm actually going to call z1. Okay, so here 0, okay, minus, what does it mean? The mean is 1 divided by, what is the standard deviation? 0.5. Okay, so -1, so I think that is going to be -2. Okay, then you're going to z2. Okay, where we want to use 1.5 now. So 1.5 minus 1 divided by 0.5. I think this is going to be 1. So what I'm trying to tell you now, so this guy can be written as, okay, instead of 0, you standardize 0, you got -2, okay, less than z, no more x, less than z, okay, less than, instead of 1.5, okay, 1, okay, and of course, how you're going to go about this, right? So where you needed to find the probability of z, give me 1 second, let me erase that. Okay, so where you want to find the probability of z, you're going to start with the upper one first, less than 1, okay, minus the probability of z less than -2. So you're going to check all of that from a statistical table, then you're going to subtract them. So the same thing you're going to do here. Okay, I think that's really make sense, I'm actually going to go to the next slide. So in the next slide, I want to talk about inverse normal distribution. In the inverse normal distribution, they're going to give you a probability, and they basically going to ask you to figure out, okay, the particular Z value. Okay, so, and that was why I said you need to first find the desired area, the probability in the body of the table. Then we then read the corresponding Z value from the left column, okay, and top row. Okay, so you can apply that here. Okay, if you take a look at example 6.7, you have a Z. Okay, let's say be the standard normal random variable. Now I want to determine the value of K such that you have this. Okay, so that is basically going to be called inverse normal. Okay, you already have your probability. Okay, you now want to figure out what is going to be the K. So if I were you, you're actually going to read out this guy from the table. Okay, what was the values of the Z-score that led us having this? Okay, so take note of that. And of course, here you also, so this is good. If you want to find this, we can say Z now is going to be inverse. Okay, going to be inverse of 0.0778. Okay, so take note of that. So we're going to do the same here. Okay, so you follow what we've done before of us going to rewrite this guy as the probability of Z less than this. Okay, the probability of Z less or equal to K minus the probability of Z less than negative 2.88. Okay, and all now equal 0.85. Okay, don't forget what you are actually looking for. You're looking for K. So you can force read this in the table. Okay, take it to the other side, add it to the 0.85. Then you're now going to find yourself in a situation like this where you're going to have the probability of Z less or equal to K equal to a particular value. Read that value in the table and check the corresponding Z score. And of course, in the case of this guy now, okay, if all of us going to do 1 minus the probability of Z, okay, less or equal to K, okay, and that guy now will be equal to 0.25. Okay, now you're looking for this guy. Of course, you know that the probability of this guy now, okay, is basically going to be 1 minus, I think, is 0.75. Okay, where you can actually, we're looking for K, right? You can read this one from the body of the table. What was the corresponding Z score? Okay, so that is what you're going to do in all of that. Okay, and of course you basically are going to be giving some other information. Okay, and don't also forget, you are more or less looking, you already know this, that at times you also know this, we may want to figure out X, so which is going to be that, right? Okay, now take a look at this. There is there's a difference between what we're doing here and what we want to do here, because here, okay, our Z is a standard normal, right, that we can check from the table. But here now, okay, it is not, because X is not standardized. Okay, take a look at all of that. That was why you were given the distribution. So before you can move ahead to solve this, you need to first standardize. Okay, and when you standardize, just got to find yourself in this kind of situation. Okay, when you standardize, don't forget your mean here is 10, right?